Good morning, everyone, and welcome to, my name is Ivashni Naidu, and welcome to the second day of the AATF Virtual Connect Conference. We again have an exciting lineup in store for you. This morning, we have Omron, and we have three representatives from Omron. Letitia Deyaka represents Omron as the Regional Marketing Manager. Werner Das, Omron FAE PM Vision Systems. Werner has a passion for systems engineering, focusing on efficient programming of any automated system. He obtained his degree in electronical engineering for the University of Pretoria and has dedicated his career to the development of efficient and reliable vision systems. We also have Evert van Janse van Vuren, is currently the product manager for CIMAC, Motion Control and Robotics at Omron South Africa. They're going to be speaking this morning on workforce retention and introduction of cobots. Before they begin, I would like to remind you to please have your questions ready and include them in the chat box provided on screen. Over to the Omron team. Thank you, Omran, for that presentation and those videos. We have some questions in the chat box. What is the unit cost, and what is what is the technical support after purchase? So, is there technical support, and what does it entail?
Hi there. All right. Thanks a lot. I hope you can hear me all right. So the unit cost really depends on the application. There's no simple answer to that. We have cobots which range from a small size to a very big size. So depending on the one you'll require for your application, together with everything else that goes with the robot, it's going to make a difference to the price. So I would recommend that you contact Omran directly, or contact myself or Werner directly, and we can look at your application and then talk about pricing. Hope that answers that question. The technical support side, Werner, would you like to answer that one?
Yeah, so when it comes to technical support, the after service, from South Africa's side, it's me and Efit that can help out doing proof of concepts for you guys, or helping with any technical questions. But it doesn't stop with South Africa. We got a whole European team that can support us on if there's any strange projects that they need to test with special capabilities of the robot side or anything like that. We can easily contact Europe. The idea is not for us to integrate the robot on every single line, but we would rather teach you guys how the robot works, and give you all the technical capabilities to be able to integrate the robot yourselves. But if you see the software itself, it is relatively, it's actually very, very user-friendly, easy to teach. It's more drag and drop than programming in the end.
Great. And then where and how do you envision these cobots working? And with already established larger robots doing spot welding, so working in the environment. So where and how do you see them working in various environments?
Right, so the Omran cobots are mainly, our main target or our main applications are for pick and place applications and assembly. When it comes to spot welding and that sort of thing, I'll be honest, from my side, there is a bit of limitation on the functionality of the robot for welding. But saying that, we have seen cases in Europe of companies using our cobots for welding. So it is definitely possible, but our main focus for South Africa is applications, pick and place, packaging, end-of-line packaging, small palletizing applications, and so on.
Thank you. And then one last question. So obviously unemployment in South Africa is a big issue. And the concern is robots will obviously take the place, or automation will affect the current employment rate. How do you address these concerns?
Ivashni, if you'll allow me, that last slide that we showed from our founder, Kazuma Tatezi, is absolutely the ideal that we strive for at Omron, where we say to the machine, the work of the machine, and to man, the thrill of further creation. As Omron Global and Omron South Africa, we're involved in projects where we help to upskill. We've spoken a lot about our project with CTC on this platform with Artisan 4.0, and we believe that even though there's unemployment, we do not want humans to just be employed in tasks that's repetitive and mundane. There's better ways of doing this, and as the industry, it is also our responsibility to help with the skills development. Although we have massive unemployment, we also have a massive skill shortage, and that is something we can definitely do something about.
Great, thank you. Thank you, Omran, for that, and it was a pleasure having you. Now moving on to our next speaker. From the IDC, we have Ingrid Govender, Senior Dealmaker in Tourism and Services. Ingrid Govender is from the Business Corporation, is a seasoned in the financial services industry at the IDC. So welcome, Ingrid.
Hi, thank you. Thank you. Good afternoon, all. I'm just going to share my screen. Okay, is this visible?
Yes, we can see it. Perfect.
Okay, thank you. Right. So I was given this opportunity to speak at the conference, and you know, it is a very industry-focused conference. And coming from a finance background, and working at the IDC, where one of our high priorities is job creation, I thought it'd be best if I delved into that topic a bit. So South Africa has the opportunity to embrace the fourth industrial revolution, or Industry 4.0, to reignite the economic growth and transformation, revitalize skills, and create high-quality jobs. This can be achieved through digitization and automation, which has the potential to create much-needed jobs in South Africa, improve operational efficiency in both businesses and government, and help deliver better outcomes for customers and citizens. The adoption of technology undoubtedly would lead to job losses. Given that unemployment today stands at its highest level in a decade, it is critical that South Africa mitigate this risk, perhaps by accelerating efforts aimed at training or upskilling of our workforce. Technological advancements through digitalization and automation could reverse the decline in economic growth and increase unemployment in South Africa by unlocking greater productivity across many sectors of the economy. For example, in metal beneficiation and fabrication, automation or robot-assisted production can reduce human error and greatly increase efficiency. In the mining sector, underground mine automation can improve safety and reduce costs. In the financial services, digitization can improve customer experience and drive greater efficiency. Such productivity gains from digitization and machine learning have the potential to drive substantial improvement of individual businesses and hence the entire South African economy. The mining industry, which has been the bedrock of South Africa's economy, contributes to more than 300 billion to the GDP and employs some 450,000 people. It is widely accepted that productivity of South African mining operations has declined over the past 5 years, even as mining companies in other regions have made rapid gains in productivity. Automation is a significant part to our solution. South African mining companies could drive real gains in productivity and margins with adoption of technology. For example, BHP Billiton, for example, has adopted autonomous trucks which operate at an additional 1,000 hours per year, and it is said lowers costs by 15% compared to conventional trucks. Another mining company has raised productivity by as much as 30% by using technology to improve the location awareness of its underground fleet. I'm just giving examples of where automation or increased digitization could provide a boost to economic prosperity. So in the retail sector, many companies in South Africa face increasing pressure on their margins, along with threat of e-commerce disruption. They also face new demands from the customers to improve their shopping experience. So accelerated adoption of technology will be a key strategic move that could improve retailers' margins significantly. Retailers could introduce digital technologies and automation into their operations to reduce costs and enhance customer experience. They can turn e-commerce from a threat to a growth opportunity. In the banking sector, South African leading players have started to automate to improve customer experience, reduce operational costs, and increase their share of the customer's wallet. Digitization is believed will create more jobs, not fewer. We must embrace technology as a catalyst to repurpose and reskill our people, enabling them to be a higher performing employees. Certain jobs will certainly be disrupted, and employers must manage this transition and help their employees to transition from their current skill roles to jobs of the future. New training and career development interventions will be needed to enable people to reposition themselves for the demands of the future. There's been much public debate about automation in South Africa and globally. Technologies such as machine learning, artificial intelligence, and advanced robotics will destroy more jobs than they create. Technology can free people from routine, repetitive work and enable them to take on higher level work or higher functioning jobs, such as decision-making and critical thinking. Research suggests that while new machines will disrupt the world of work, overall it will create more new jobs than it destroys. If we look back at history, technology has created large shifts in employment, but the increased productivity it ushers in generally creates many more jobs. The introduction of personal computers in the 80s destroyed an estimated 3.5 million jobs in the US, for instance, amongst typists, but it's created 19 million new jobs right across the economy. In South Africa, we estimate that the digitization, machine learning, and automation have the potential to create approximately 1.8 million new jobs purely as a result of improved productivity, which in turn could increase income levels, consumer spending, investment in construction, and infrastructure. An additional 1.2 million jobs could be created in unknown occupations created through technology advancement. Here's some concluding remarks on this topic before I just take you through a couple of case studies. South African decision makers across sectors need to take bold steps to ensure that there's sufficient reskilling to help reabsorb workers into the workforce. They also need to strengthen the education system to generate the technology-related and life skills which are needed at sufficient scale. Only with these actions will South Africa successfully manage the massive workforce transition ahead. Indeed, these steps are essential if the country is to seize the potential of technology to unlock inclusive economic growth, improve productivity, and reduce the country's unacceptably high unemployment levels. Following are just two investments that the IDC has made in the last 2 years and these are pretty much companies in the automation space or IoT space. So the first one is a company in Cape Town called Data Profit, which offers a software service manufacturing optimization platform, which predicts and eliminates defects or scrap rates in a production process and improves yields. How this is achieved, it's an AI system that uses process data and to proactively prescribe process parameters to the equipment, and thereby improve overall yields, reduce waste, and improve product quality. So Data Profit's technology has application in various across industry verticals. Just a couple of examples that come to mind. They have an installation at Atlantis Foundry in the Western Cape, where they were able to, through analyzing of historic data, their intervention has improved or reduced the scrap rate from 6%, which was the historic average scrap rate at that plant, to a 0% defect. Now, this has huge gains for the company, but also in terms of their customer. The biggest customer they have was Cummins Diesel, where they were producing engine blocks that were being shipped to the US. And by reducing the defects, they were, also assisting or saving the customer down the line from defects that would arise, at a later stage. So Data Profit has since partnered with a foundry equipment supplier, and this partnership has, along with IDC's investment into the company, allowed the company to expand to the the other example I wanted to, so these are some of the implementations that Data Profit has in a couple of sectors, mostly in the manufacturing space or mineral processing. The other company that IDC has invested in, a company called Genemark Automation, which has been around for a while. Genemark approached IDC around 2 years ago when they were looking at commercializing an Odin system, and IDC subsequently invested in the company. The Genemark has operations in Europe and India, and the Odin software that they had developed was internally generated, and the company approached IDC then to assist them with further developing the capability of the Odin software, and then the commercialization of that. So just for example, on a plant that we visited in India, it was Mahindra Electric. What was impressive was at a plant where they were assembling these electric vehicles, the Genemark produced the entire assembly line, and the assembly line was then supported with the Odin software as an overlay. And what was impressive to me was you would have an operator assembling a component, and who was being guided by the software to the point where they were able to reduce the defects that come out of an assembly process. So it's almost enabled a human being to operate as a robot. So it would guide you on whatever needs to be selected, how much torque to apply to a specific bolt, and take you through the process. So it's a guided assembly process. So for me, what was impressive is that in an instance like that, using automation didn't actually destroy the job for the human, but essentially made the human more efficient. And those kind of applications yeah. Okay, so okay, thanks. I'm done. Thank you, Ivashni.
Thank you, Ingrid. Don't seem to have any questions at this stage. Just wanted to find out if you'll be able to put your email address in the chat box so that any attendees after the event would like to contact you to just get some answers if they have any. And thank you so much for joining us this afternoon.
It's a pleasure. Thank you. I think I'd just like to take this opportunity to invite some of the attendees to approach us. I'll put up my contact details. To talk to the IDC on some of the projects that you're working on. Would be keen to look at how we can assist if there's a role for us to play. So I will definitely share my contact details in the chat. Thank you.
Perfect. Thank you. And then just also a reminder to please just put your questions in the chat box so that we can address them with the speakers after their presentations. Also, we will have a poll running as well during the course of the session, just so that we can just get some insight as to what you feel regarding AATF. And then we just going to move on to our next speaker, Mr. Colin Morris. And Mr. Colin Morris is from Africa Weather. He's the head of sales in Sub-Saharan Africa and the sales manager for South Africa. And his topic this afternoon is automating weather controls into your operations system. Thank you, Colin, and over to you.
Thank you. Can you hear me perfectly?
Yes.
Excellent. Thank you. Thank you, and good morning to everybody. I'm going to start off by sharing my screen. My screen showing?
Yes, all good.
Excellent. Thank you. Good morning, everybody. Good day to everybody. Yes, the discussion here is automating weather controls into your operating system, operational system, whatever system. Weather is definitely a topic that all of us are talking about. We've all seen weather change. We've all seen weather differences. And we know that weather impacts big operations to small operations. So uncertainty, it's one of the worst feelings anyone can ever feel. Not knowing is bad enough on a personal level. However, when it comes to business, the stakes can get very high. Uncertainty in budgets, in planning, and deals create a lot of stress and potential loss. This is especially true for mining and industrial operations. So the biggest problem that I'm talking about here is mining might chiefly be what comes out of the ground. But when it comes to safety and protecting assets, some of the largest risks come from above. Now, I'm going to focus mainly on mining and automation around mining, etc. But I'll touch on it a bit later. Again, anybody who plays golf, anybody who lives near a school would have heard light sirens going off. I know that lots of golf players don't like us because we kick them off the golf course early and they think they can stay longer. but really the fully automated lightning system that is going off and warning them is warning them for safety issues. The weather presents some challenges, hazards to safe mining operation. Lightning poses a risk to personnel involved in heavy equipment operation, explosives handling, and construction activities. Mainly, we've seen this at the top of slimes dams. We've seen this at the top down in open pits. We've seen lots of lightning happening all over the place where people have been injured. I've been personally experienced in lightning fatalities in northern Zambia, and lightning causes huge amount of downtime, huge amount of problems with the DMR, and huge amount of problems with the statutory obligations of the mine to make sure that people are safe. So by fully automating a lightning and a weather solution will mitigate huge amounts of those problems. So with effective planning, the disruption caused by adverse weather can be minimized and risks mitigated. Mine operators can now proactively and effectively manage pending storm risks with technology which tracks observed lightning, fully automated, delivers proximity alerts, fully automated, and forecasts activities over the coming hour or 7 days. So the inclement weather warnings can be fully automated, are fully automated. The nowcasting and the forecasting is fully automated, and we can automate DMR requirements. The interesting part about that is that DMR needs to know how much heat, how much cold, how much rain, how much lightning took place over a period, and if there's unfortunately a fatality or an accident, DMR also want to come in and discover and talk about that. The inputs to the system are automated weather stations. So those automated weather stations aren't just a toy. Automated lightning networks and lightning sensors, satellites, radar, and models. So those inputs we take and put into an automated weather portal, which is a web page. You can see a picture of that on the right-hand side of the screen. However, the most important decision that anyone makes when they're going to get a weather company to give them details of the weather is where are they getting that information from? How accurate is that information? Because there's lots and lots of free weather information, and how up to date is that information? For example, that models, the ECMWF, that is freely available off the web. However, generally, because you're getting it freely off the web, there's a time difference between it. Outputs, web page, SMS and smartphone app, audio-visual alerting, forecasting, post-event tracking. So the outputs that what I'm talking about here are the fully automated web page, SMS and smartphone app, meaning that as lightning enters the predefined area or as hard winds enter a predefined area, so you will get a warning via SMS or a smartphone app, and audio-visual alerting, which is a siren, the one I mentioned a little earlier that you see at the golf clubs, but you certainly see them all over the mines. The forecasting, which is great for production, great for safety. You see that there's a huge storm coming in. There's flooding effective in the next 5 to 7 days. You don't send out your $1 million piece of equipment into the field. And if there's any issues around an accident or a fatality, we can also do post event tracking of any weather activity. Weather risk management, monitoring the skies for specific weather risks and warn clients to respond. So what we do is we monitor, track storms, grounded lightning strikes, and storm activity that might be of interest to you, the client, or to your clients. We generate notifications, immediately inform our clients on how your operations will be affected, and then you can respond. So a SOP, standard operating procedure, is put in place, that at a particular warning, something happens. If it's high masts, the high masts get dropped. If it's working out in the open, people don't have to go into the lightning shelters. Excuse me. If it's flooding, flood risks need to be taken into consideration. One of the interesting things about this automated system that I'm talking about here is that we monitor both cloud to ground. We monitor all three: cloud to cloud, cloud to intra-cloud, and cloud to ground lightning. Why? How do we do that? Why do we do that? Because we have a total lightning network in South Africa, and we have a global lightning network in the rest of Africa, and are able to do global light network throughout the world. Anatomy of lightning. I'm not going to go into too much detail around this, but because we all really know what lightning does. And sadly, I know of at least 3 fatalities that happened in Joburg over the last 3 or 4 years. So that should never have happened, because people need to understand the lightning. So it's really a very basic piece of electricity that the lightning forms, bolts down, and causes damage. What are we able to do? We measure cloud to cloud and cloud to ground lightning. Intra-cloud lightning is sometimes called sheet lightning. Cloud to cloud lightning between 2 separate clouds, and cloud to ground, which is the dangerous one. Why do we measure the first 2 points? We measure them simply because they are the precursors to the cloud to ground, and an operation that is running automated is able to make decisions based on what is incoming. There's a mine up in West Africa that we installed a complete system with a weather station, with lightning sensors, with automation, and they are a fully automated mine. They bring their entire mine to a standstill when they get lightning in certain areas. What are we able to measure and give out? Well, this is a typical example of a mine in Nigeria. Between March 21 and April 21, there were 1,590 grounded strikes in the area. Their highest peak current, so we could tell the grounded strikes, we could tell the current, and we could tell them from the center point. That's what it looked like in a map of a Google map of all the grounded strikes. The midpoint there, that little blue hut, is the center point with all the grounded strikes around it. And when people realize what is going on and how dangerous it really is, all of us see lightning, none of us realize how dangerous it really is, but there it is on top of them. Africa weathers total lightning network across South Africa. So from an automation point of view and a completely standalone, and I love using this word, in the cloud description of lightning, we own, manage, and maintain our own lightning network. That lightning network is spread around Southern Africa or South Africa, that then talks to a server. The lightning in the area is determined, sent to the server. The server uses algorithms and then sends that information to the web page. In the beginning, I mentioned about how all this data is acquired. Clearly, we're using lots of partners. What we take is we're using the different partners. So here are 4 or 5 of them. South African Weather Services, our biggest partner. EUMETSTAT, the satellite partner. Earth Networks, our lightning partner. Weather Zone, the web page partner, and ECMWF, the weather partner. Each one of them, the details are inputted into our different web pages, lots of algorithms and information put behind it, and then a fully automated forecast and nowcast is produced on the web page. I'll be showing you the web page in a few minutes. That there gives you an idea of the global view of lighting. Clearly, we're talking about Africa. This was done on a particular day, and you can then see the global lighting around. How's it done? So how's it done is that there's a network sensor placed around the world. In our case, I showed you the picture of Africa. We have these network sensors. These are the network sensors. They monitor the lighting in the area. They have a GPS antenna that makes sure that we have records that transmit lighting flash waveforms and have TAO, time of arrival method. So we are able to very accurately define the time of arrival, the height, the value of the waveform, so that a clear decision can be made by the operators. So with lighting alone, we can give a location and a timestamp. We can give peak current. We can give polarities of the cloud to ground strikes. We can give intercloud. We can clarify the difference between intercloud and cloud to ground. We can see flash multiplicity, the height of the intercloud estimate, location of accuracy estimate, and many other parameters that are required in a normal weather situation. By using total lightning, we're also able to monitor severe thunderstorms, high winds, hailstorms, microbursts, tornadoes, cloud to ground lightning. So anybody who's got a car insured with one of the bigger insurance companies would also be receiving hail warnings. Please move your car underground. Please move your car inside. There's a big hailstorm coming. That is also one of the options that we have, one of the products that we supply. We're able to measure the incoming hail and give a warning automatically. That's the total lightning network globally. I touched on it a little earlier to give you an idea of the feel and the overview. And we're able to do DTAs. DTAs is a dangerous thunderstorm alert. So in South Africa, we're able to give a dangerous thunderstorm alert, which means that the highest probability of heavy rains, hail, high winds, squalls, lightning strikes, etc., solely because we own, manage, and maintain our own lightning network, and we have that ability with using that lightning network. Opticast, that is our real-time observations and forecast. So this is Opticast is continuously optimized in real time and is a 7 or 10 day forecast. What it does is it's using 30 parameters inputted. The algorithms are then defining how the outputs are, and depending on the operation. So there's an operation I mentioned just now in West Africa that has a particular problem with high temperature. They monitor the temperature as well as lightning. There's an operation in Zambia that monitors flooding and high rains. So depending on the operation, each one of those operations parameters can be set up in the Opticast. It's called the robot system because it's green, orange, and red. Red obviously means that you've now reached your parameters of danger, and this is a very accurate 7 day forecast. So for a operation that is using that needs to bring the operation down for maintenance at different times, they can do this automatically. They can see that there's going to be high rains in 5 days and then plan a production stop or plan a production maintenance, and that can all be done automatically. One of the questions that we regularly get asked is how accurate is the system? Well, the lightning system is continuously verified against NOAA and NWS, and it's ongoing impact-based comparisons. We continuously do that, and we in South Africa regularly measure it against any other lightning networks that are available to make sure that we're always accurate. Automating weather controls in your operating system. The controls, company-wide SOP. I mentioned that just now about getting the two role players on board. The two role players clearly are production and safety. So there must be a company-wide operating procedure where they know that if X happens, Y is put into place. Check and production must be on the same page. The beauty about this automated system is that the user interface is 100% customizable because it's all web-based, cloud-based, as I'm showing a little bit on the right there. The automation output is personnel warnings, so that would be coming via an SMS or a smartphone app. So that as well is automated. There's no human interface. That golf course that I was mentioning earlier, the beauty about that is that you don't have to have anyone setting off alarms or sirens. It's 100% automated. Another option is an API, that the web page can talk directly from an API to a PLC to the warning device. There's a particular mine in Middle Africa that has got this API, talks to their PLC, and once they get a big storm warning, they automatically slow down or bring down the cranes that are on in the higher working areas, and that's fully automated. And then, of course, an MES system. So the same thing applies, is that you could be using your management execution system to measure how much downtime was caused due to the lightning, how much downtime was caused due to weather issues. So what we've also done on a mine in Zambia is that we've inputted all of the weather data directly to an MES system, and that then gives them a complete output and view of what they are looking at the end of every month, and they can then successfully say that they were down because of lightning, or they were down because of flooding, or down because of rain. And then the audio visual alerting is, again, back to the top there, is a siren, a light, something that is 100% automated and able to warn people about what is going on. Could you please confirm that you can still see the screen?
It's just buffering at the moment.
Okay, so this is what the web page, thank you. This is what I can now see it, thank you. This is what the web page looks like. This is an overview of the web page. What I'm showing here at the moment is our lightning network. The green and red and orange dots there are the lightning network within South Africa, the total lightning network in South Africa. As can be seen there, we have no lightning at the moment we have no lightning in South Africa, but in northern Botswana over there is active lightning. You can see the active lightning happening. And if you want a thunderstorm forecast, that's a clickable. There's a thunderstorm forecast. So there's expected thunderstorm possible in middle Mozambique, very possible in the middle of Botswana, and possible in northern Botswana. Thank you. I think I've taken too much of your time. If there's any further questions, I'm happy to take them.
Thank you so much, Colin. You didn't actually take much of the time, but thank you. We did have one question for you in the chat box. Can you provide a weather as a service API plugin that can be used in other software applications?
Yes, yes. I covered a little bit about that. So we're able to supply an API directly out of the web page that can talk directly to a PLC and MES or to another web page. So the insurance companies use our APIs. A mine in Zambia uses the API. So yeah, without a doubt, it can be done.
Great, thank you. And then that was all the questions that we had, but if I can also ask you to please add your details to the chat box. So if anyone wants to contact you post the event, they can do so with any questions. And then next up, we have my colleague from AATF, Dillian Philby, who's going to give you a brief overview of the event. Over to you, Dillian.
Good afternoon, everyone. Thank you very much for that introduction, Ivashni. Yes, some exciting speakers today. Thank you, Colin. That was most informative. Yes, I'd love to obviously invite each and every one of you to partake in the 2023 live event of Africa Automation Technology Fair, which is the largest showcase of industrial automation, smart control technology, and the future of digitized manufacturing. The event is the go-to show for all automation and technology on the continent, and you can't afford not to be there. So it's the chosen platform in Africa that brings together automation and technology industry experts, vetted buyers, engineers, project managers, technical professionals, mining executives, and government across the African continent. 2023 is themed from Africa for Africa. We offer maximum exposure pre, during, and after the event in the form of webinars, our monthly e-magazine, social posts, and emailers to our extensive AATF database. This is to connect and aid you into increasing business with face-to-face interactions, demonstration areas, CPD accredited industry talks, and valuable content from both local and international experts in the automation industry. The event offers an opportunity to build relationships with your current and potential customers. It's evolved and includes some exciting new product categories in the form of artificial intelligence, cybersecurity, robotics, integrated industrial automation, digitization. Exciting digital opportunities have also been designed for you to enjoy and complement your existing marketing activities. So I'm inviting you to sign up today, secure your space, and we look forward to having an in-person interaction with you in May 2023, the 9th to the 11th of May 23. Hope to see you all there. Thank you so much.
Thank you so much, Dillian. And I just want to remind everyone, I wonder if, oh, Colin is not around. So Hermias, I just saw your message in the chat box. Colin did address the question and he did say, yes, the plug-in service is available and it is being used. And one of the examples of application that he used is that it's being used in a mine in Zambia. But he did put his details in the chat box as well if you wanted to get a more comprehensive answer on that. And then I just want to remind everyone to obviously please make sure that you complete the poll, which is currently running. And next we go on to our last speaker for this virtual Connect series of our two-day conference. And the topic is hybrid manufacturing technologies, and it's going to be presented by Dr. Jason B. Jones, who is the pioneer and the world's leading authority on hybrid manufacturing, integrating additive manufacturing with a mainstream CNC machines. He is the He is a co-founder and CEO of Hybrid Manufacturing Technologies, transforming CNCs and robots into flexible smart factories with additive, subtractive, and inspection capabilities. Dr. Jones has a PhD in 3D printing from the University of Warwick and has led millions of dollars of AM development and commercialization. He is the author of numerous publications and a distinguished inventor holding dozens of patents. Thank you, Dr. Jones. I know it's good morning for you, and thank you so much for participating today.
It's an absolute pleasure to join you all, and it looks like it's been a fantastic event so far. I do join from Texas, so where I'm at, it's morning, and good afternoon to each of you, and if you've got anybody in between. So I'm pleased to be able to speak with you. I'm going to use my video feed to also share my slides. So if I'm already not kind of full screen in your browser or your viewer, please make that full screen now, and hopefully you can see some images. So, as introduced, I'm pleased to be talking about hybrid manufacturing. Hybrid manufacturing, for a lot of people, and it gives the opportunity to modernize manufacturing. When I say the word hybrid manufacturing, some of you may have imagined a combination of processes that look like this. On the left is CNC machining, right? If you're not familiar with machining, it's a super duper version of drilling, but it's a subtractive technique where you start with a block of material and you remove it. I'll give you some more examples as we go forward. And on the right, you can see an image of laser metal deposition, which is actually adding material. So again, more details to come on that. I join you from a company called Hybrid Manufacturing Technologies. This is our specialty and what we've spent the last personally, I've spent at least 15 years on this, nearly 2 decades. So, okay, a little bit of history about making things. This is a poll question for you. True or false? Additive manufacturing initiated the digital manufacturing revolution. I'll give you just a minute to think. Additive manufacturing initiated the digital manufacturing revolution. The correct answer to that is false. Although 3D printing has done an awful lot for digital manufacturing, it was not the first technique. And let's just go on a little timeline, right? And one of my favorite places is Egypt, obviously in Northern Africa. And back nearly 4,500 to 5,000 years ago, we see the way that these were built was layer upon layer. It was an assembly technique, if you will. And 3D printing or additive manufacturing borrows some of those same principles. Obviously, it's at a much smaller scale, but it borrows this concept of building layer upon layer. Now, if you'll notice carefully on this pyramid at the very top, you'll notice that it looks a bit smoother than what's lower down. And they actually would build this up layer by layer. It would be, they'd have small steps on the outside which fit the stone. And then they would cut a softer stone. They'd cut limestone and put like an outer layer, like a veneer on it. And that was a finishing technique. And they made it so smooth, they said that it would reflect the sun's light. In fact, that it was so, in the top actually had a mixture of gold and silver on top of it. And it was so bright that when the midday sun would hit it, you couldn't even look that direction. So a really interesting combination of techniques for making things. If I skip along, oh, and this reminds me of one of my favorite little, it's just a bit of a parody, but you know those goal and achievement posters? I like this one. You can do anything you set your mind to when you have vision, determination, and an endless supply of expendable labor. That's from despair.com. I just think it's kind of fun. Okay, moving on to the next thing that we make. Well, not the next, but one of the next things. This is Petra, which is in Jordan in the Middle East. And if you look at this carefully, this is actually carved completely out of the cliffside. There was very little, if any, addition of material. This is purely a large piece of stone that's been cut and made into this shape purely by removal techniques. So again, bearing in mind we've got an assembly technique and a removal technique, and now we look at digital manufacturing and kind of take those examples forward with us. Really, it was the 1970s when CNC machining started to enter the scene and become significant, and then there was a significantly higher adoption as we move into the 80s and beyond. CNC machines they are a box, they have a cutting head in them, and it really was what launched the digital manufacturing revolution. Sometimes I hear people say, oh, 3D printing launched the digital revolution for manufacturing, and it certainly helps, but it's not the original digital manufacturing technique. When we talk about 3D printing, we're actually talking about a group of 7 different types of physics and more, but specifically 7 that are standardized according to ISO and ASTM and some other standardized bodies. Each of those 7 flavors has different pros and cons. We'll get into a few of them later on, but just be mindful that that term is an umbrella term, and you may have a small desktop machine that we call a 3D printer. You may also have like a refrigerator or maybe even a room size printer that's also referred to as 3D printing. They may be doing, using different sets of physics, but it's all part of 3D printing. So that really was innovated mostly in the 80s and started to gain adoption, traction, starting around early, late 80s, 1990s, something like that. When we talk about 3D printing, it's important to remember 3D printers very first were innovated to use polymers. And so the parts that were made were plastic parts. Since about the 2005 to 2010 period, we've seen added momentum and capability to be able to print things directly in metals. And that has really driven a lot of the industrial adoption beyond just prototyping and really moved it into end-use parts. In 2013, commercially, we initialized the first combination of these 2 techniques. And so CNC machining and 3D printing, certainly a 3D printing from a directed energy deposition standpoint, that was the first time they'd really been merged and made commercially available. There was also some parallel work in Japan that worked on powder bed fusion that became evident around this same time to the rest of the world. So that's just a brief overview of digital manufacturing, so you can state correctly. I would summarize that 3D printing has added a lot of fuel to the fire of digital manufacturing and certainly made it very accessible and made it into the public eye. So this is a timeline of what has happened in the hybrid manufacturing space from the early days. It really started off with the initiation of this industry. I will share a link to it with you a little bit later in the session if you can stay with me. Okay, so again, to emphasize, CNC machines initiated this digital manufacturing revolution, and then additive manufacturing continues to fuel it. Now, what is CNC machining? CNC machining is a process where you take a block or a billet or a solid bar of material. In this case, we've got a little bit of aluminum here on the left. You then remove from it chips. And that chip removal process is done by cutting tools, often mills, milling cutters, or end mills, some people call them. You got a ball mill on the right. So a variety of cutters that literally will cut away small chips and carve away that block until you end up just with what you want. And I have here shown on screen just a small pawn chess piece. Now, this is a picture of cutting in process, and you can see each of these little diamond-shaped inserts, they're called, is actually scratching away or carving away the metal as you work. Here you can see another live shot action where, again, you see these blue chips on the right of the image. That is being cut and removed away from this block, and we'll see a little bit of milling later on live as well. So that's milling. When you do milling or subtractive machining is the general term, you always have to start with a block of material that's larger than the final part that you want to print. I love this quote from Harvard Business School, and it just emphasizes that machine tools are the mother machines. That term I hear most frequently in Japan. In the mother machines, in that they make all machines. Every manufactured product is either made by a machine tool or made by a machine that was made by a machine tool. Thus, at the heart of the industrial health of any nation is its machine tool industry. By the late 1980s, additive manufacturing joined CNC as another digitally driven technology. So before the 80s, bear in mind, CNC machines were like the very foundational layer of how do you make almost everything. CNC machines would make it or make the tools that made it. Now we've got CNC being joined by additive or 3D printing. Again, here's a little closer view at those additive families. If you would like a little quick reference chart on our website, if you go to hybridmanutech.com or type in hybrid manufacturing technologies and look on the resources page, you'll be able to download a PDF. And it gives an overview. Each of these colors represents a different set of physics, and there's pros and cons to all of them. That's why they all exist. And there's actually, 7 categorizes the vast majority of 3D printing. We've had a few that are sort of combinations thereof that are proprietary that now kind of fit a little bit outside of these categories, but this will get you 90% of the way. Again, most of these were innovated around polymers, and now almost all 7 of these can also be used with metal if you have the right printer. So this is a quote, when I first saw metal parts made by additive manufacturing, I discounted them entirely. I thought that the process would never be able to catch up with the quality of CNC machine parts. That was me. I still remember I was at an exhibition. I saw this glass cabinet. They had parts inside. And as I looked at them, just looking at them, they didn't look very good. When you CNC machine something, you have cut beautiful smooth surfaces. Everything's shiny. It looks very intentional. And when you 3D print something, normally there's some texture to it. For metal parts back then, it was quite rough. It looked like very rough sandpaper. And I didn't get the impression that this was a quality or well-controlled manufacturing method. And I just thought, this isn't going to catch on. And yet, here I am later, having repented of that clearly. So the additive process conceptually, and this happens to be a representation of one of the 7 technologies known as powder bed fusion. It's widely adopted in industry. So here you start with an energy source. You bring to it some kind of feedstock material, either wire or powder. It does not need to be larger than your final part. In fact, it will always be smaller than your final part, almost always be smaller than your final part. You then melt or fuse or consolidate that material together. Here you can see spread out on a build plate is copper powder, and that light is where a laser is hitting it and fusing together the copper. And you end up with a final part. I'd like to show you a little video. This video is not a laser-based process. It's an electron beam process. And here they're preheating a bed of powder, so spread out powder. And then you'll see they're actually tracing around the outer profile of a cross-section of that part. So before your eyes, what you're seeing is this powdered metal get melted and then re-solidified, and you can see the shiny part. That is an actual cross-section of a part, and it will do this over and over and over again. So as soon as it's completed scanning across this layer, you'll spread another layer of powder on top of it, and that energy source melts the powder on top, and it melts it just far enough to melt into the layer beneath it. And that's how you get this layer upon layer process that we know as additive, hence the term layered manufacturing for some people. So with these 2 new digitally driven technologies, the big question has been, are they rivals or are they complementary? And if we look a little bit more in detail at what the CNC machine might look like, here's a picture in the bottom left of an actual CNC machine. This is an early style of CNC machine from one manufacturer named Haas. It's become quite popular, at least in North and South America, but in many parts of the world. And so that's what a CNC machine looks like. You can see the pawn again that I showed you earlier. Something kind of interesting, you can see a 7-to-1. That's a ratio. What we're showing here is that you're purchasing, in this particular parts case, you purchase about 7 times more material than what ends up in the final part. In the aerospace industry, people refer to this as a buy to fly ratio, because your parts that end up flying, often there's a significant reduction. You may buy 7 or 9 or 10 or even sometimes 20 times the amount of material that will end up in the final part, but you have to start off with this block of material. And so there's not another easy way to do it. And what that ends up as is CNC machining is a fantastic process. It's highly repeatable, very precise. You end up with nice shiny surfaces, and it's very productive. The only catch is it's quite wasteful. And depending on what part you're using, it can be very wasteful. Other times, not so much. So then taking a closer look at 3D printing or additive manufacturing, here again you see a fairly early version of a powder bed fusion machine. You can see a part that's been printed in it. And if you look down at those numbers at the bottom, you see 1 1/4 to 1. The waste involved in 3D printing is significantly lower. And so this difference in ratios in these two examples, right, 7 to 1 compared to 1 1/4 to 1, there's a big difference in how much you utilize of that feedstock material. And so for additive, one of the pros for it is we see far less material wastage. That's not to say it's zero. Everybody that does additive manufacturing is working to improve that, but it is there's a far higher yield typically for the feedstock material. You get a lot of freedoms. By printing layer by layer, you can make some complex geometries that are difficult to cut from a solid block. You can also sometimes vary the materials. So you may be able to change the composition of your part, which is really exciting because it allows you to put, maybe the outer area could be higher wear resistant material or survive higher temperatures, while the inside might be a lower cost base material. Now, additive manufacturing has a couple of cons as well compared to CNC machining. Just as a volumetric statement, you tend to have longer cycle times. Adding metal, especially metal, but material, tends to take longer than removing it. And also, the surface finish is relatively poor. There will almost always be some texture there that needs to go back and finish. So as we compare and look once again at this, are these rivals or complementary? And you look at the pros and cons of each, what we decided many years ago is that in many cases, these are complementary technologies. Occasionally they compete, but especially when you look at surface finish, where over here on the left, if you look at a pyramid style shape, you can machine a very, very smooth surface if you take the time to. With 3D printing, your intended surface is anything that's curved or angled is always approximated. And you'll end up with this we call it a stair-step effect, this layered manufacturing. And as a result, you've got to come back and either fill in those gaps or cut off the high points to be able to get to the same level of surface finish. And if we look here closely, these are some examples from Bathsheba Grossman. She's a digital artist, one that I really like. And if we look carefully at these parts, they've been 3D printed. And if you look, you can see what looks like contour lines coming out. And that is that stair-step effect on the surface finish. So the stair-stepping effect, when we 3D printed primarily in polymers, it was not such a big ordeal to smooth out those surfaces. It could be done with sandpaper. It could be done fairly quickly. But as we moved then on to making parts from metal, this became a far more significant issue. I often call 3D printed metal parts and high density parts, high density material parts, unfinished parts. When you're done printing, they're not normally suitable for interchangeable parts. The tolerances aren't normally met with high enough precision, and the surfaces are not smooth enough. And I'm showing you here an extreme example. This is an image of a printed part using directed energy deposition with an electron beam. This is a part by Siaki. And if you look at it carefully, I always describe it almost as having a characteristic that feels a little bit like marshmallows. It's very soft, it's very rounded, They've done a great job of ramping up the deposition rate, but then they rely on machining to come back and give that approximate form or near net shape its final defined shape. And this is good practice, especially as you scale up in the size parts you want to make, letting 3D printing handle the internal and the volume, and getting only close on the outside shape, and then letting a second process take care of the rest of it. This is the way almost all metal 3D printed parts are produced. They require some finishing, machining, grinding, polishing, something like that. So, again, reviewing this kind of comparison chart, our view is, particularly as we get to, as you look at trying to get layered processes to go faster and faster, you end up with this dilemma. You say, okay, I can take my deposition process often and scale it up by going with thicker layers. That increases my volumetric deposition rate, but it gives me a problem. If you look on the left, that increased productivity actually is detrimental to the surface finish. So you're making one thing better and making another thing worse. One of the printers I really like in its early days had a version that said you can run it in high quality mode or high speed mode. And I was always like, yeah, but I need both. I want both. And so to help resolve this dilemma, for us, often in 3D printing, people who only have access to 3D printers will go for this improved surface finish on the right, but it increased cycle times by double or even triple sometimes. To help resolve that dilemma for us, we said, hey, we realize that metal additive manufacturing does not work without CNC machining. So why not merge these together and try and leverage what each is best at and try to skip over all of the negatives for each of those? And for us, that is what a hybrid approach is doing, is combining these two capabilities into, in our case, into a single machine, so that you can do either one whenever you need. So I hope that's given you a little bit of background about the history and why metal removal and metal adding, and certainly polymer and ceramics and composites, all of these have the same trends. I show metal because industrially it's really desirable. You can do some very high-end parts that are high-performance parts, I should say, that can be adopted into industrial use and implemented readily right now. So all of these material sets, as you push additive to do more and more, you're going to find the need to be fluent in adding as well as subtracting. Now, let's dive in for a little bit of history, right? As we kind of transition over the last several decades, we see what have historically been separate machines, and you can see the silhouettes of manually controlled machines here, from 40 and 50 years ago, that many of them are still in use today. Lathe, mill, drill press, all of those sorts of things. And they have actually merged, that capability is largely merged into single machines. Sometimes we call them multitasking machines because they do multiple subtractive operations. And they're computer controlled. So that's a wonderful step along the digitalization. And I hope today, throughout the last 2 days, as you think about digitalization, CNC control and CNC machining has come to the front, and if not, I'm pleased to highlight it now. Okay, as we then move this trend forward over the last, mostly within the last decade or so, we look at this convergence of technologies now includes additive manufacturing. And so as we merge those together, and even inspection in many cases, as they merge together into a single setup, we call this hybrid manufacturing. It can also be used sometimes with multiple machines in like a hybrid type cell. But hybrid machines specifically, that term is most often applied when you're able to combine them all together. So just a little brief, why am I even here and why am I talking about this? We have pioneered the use of two types of additive: directed energy deposition, abbreviated on screen as DED, and material extrusion in combination with CNC machines. And you can see below some different types of heads. These are all deposition heads, and their form factor is important because it allows them to be used in existing CNC machines. We'll talk a little bit more about that in a little bit. Because we innovated in this space, we are the most adopted in terms of hybrid machine models worldwide. And a lot of this is because we have this open architecture. So we're able to intermingle multiple different technologies. So that's just a little bit of why I'm here and why I'm talking with you. But let's jump back into the technology itself. How does it work? Usually we'll take a base platform, either a CNC machine or a robot, and we will then add to it the components required to be able to do additive. So in this case, this is a head for polymer or composite extrusion. You can see on screen here, it fits in this on the left, it's fit into a CNC spindle. Normally that spindle would be holding a cutting tool and rotating. In this case, we're going to use the power of the spindle to drive the extrusion and make parts very, very quickly. You may have seen this process at desktop scale. Hopefully you have access to a 3D printer. This runs between 200 and 2,000 times faster, depending on what your setup is and what materials you're using. It can also be used on robots, and here we see this is Autodesk, who uses this technology within some of their research facilities. So here's a short video that introduces this concept of how it works. These deposition heads can be loaded into a spindle. There you see a manual load. It can also be mechanically loaded automatically. And you slice them as you would a 3D printer. The code that comes out is then the same code you would use on a CNC machine. And here you see a deposition. The deposition width on that right there that you're seeing go down is about 8 millimeters wide. So it is not a small, in this case, it's not small scale. It's been scaled up for industrial applications. And you're able to do large format parts very, very quickly, up to about 9 kilograms an hour. So a fun use of CNC machining to also do 3D printing. The same philosophy applies when looking at doing metal deposition. These are heads that use metal, either powder or wire. They can be integrated into, again, a CNC machine, with some different, in each case, you've got the heads. It's not only the heads, you've also got a way to manage the feedstock, whether it's powder or wire, and you need an inert shield gas source, since it's essentially a welding technique. Here it is, again, set up on a robot, a little closer view for you. And if you watch this video here, this is a partner of ours, Mazak, and you can see 3 deposition heads all doing metal deposition at the same time. The way this particular machine is set up, you can actually change between different heads so that you can do whatever technique is the most time effective and cost effective for the features that you're working on. And here you see this spiral has been added onto just a raw bar. When you're done, you can also then transition to milling and cut these different parts so that you end up with a smooth surface. And this is a prime example of hybrid manufacturing. This is an oil and gas inspired part. So I hope that gives you a bit of an idea of how these machines are put together, what their architecture and anatomy is. And let's look now at what you do with it, right? It's the application space that really drives the development of these systems. So here's a little table of different opportunities within 3D printing. You'll notice from left to right at the top these icons: coding, repair, adding features, and growing parts. And some of you are saying, hey, why are you talking about coatings and repairs if we're talking about 3D printing or additive manufacturing? And my response is that you are adding material, and actually many of the business opportunities to add a little bit of material rather than grow the whole part from scratch are really, really strong and can be adopted immediately. And so some types of additive are especially well suited to being able to do these other things in addition to building parts from scratch. So how are all of these things done? The way we approach it is that we have this modularized digital manufacturing tool range. And if we look carefully, you can see inspection style heads. These logos kind of indicate their capabilities: inspection, subtraction, and additive. And as you walk around and look all these different heads, They each do something different. So you can do laser line scanning or eddy current inspection, and especially, of course, on the right, you can do additive. So material extrusion, directed energy deposition, syringe extrusion, and some others. So you then call up the different deposition head that's the most suitable for these different applications, and let's look at a few of them. So if we look in the coating space, if you look carefully at this part, you can see this is a bronze substrate, and it's got the edges are silver in color. The actual material that's been deposited there is a superalloy it's a metal matrix composite, actually. So it's a superalloy base with high performance oxide, basically oxide sprinkled in, so that it's a very wear resistant coating. Metal matrix composites are really a great material class, and it's something that we can add. So the only additive step in this case has been those edges where it looks sort of gray in color. If I skip forward here, this is an oil and gas part, and you can see there's sort of a V-shaped, cutout here. In that V shape, if you look carefully, you'll see two different colors of gray. And the base material here is steel, F22 steel, and then Inconel 625, which is a nickel-based superalloy, has been added into that V channel. By adding that coating on the inside of the channel in that custom shape, you can often double or even triple the lifetime of this part. So if you've already been through the hassle to make this part, and let's suppose the base part has cost you something like, 100 or 150, then you could add this. This is an incremental 15 minutes. So you may add an additional, 20 or 30 or 40, something like that, in your currency to add this additional coating. But if it lasts twice as long, why not invest the incremental 15 or 20% to make something that's twice as good? If you look at this part carefully, up in this upper half, you'll see a trapezoidal shape. That is actually a pocket that has been filled in. For decades, CNC machining has been cutting metal and polymer and other materials. And if you cut too much, you're in trouble. You normally have to scrap that part and start over. Here, we're able to actually recover that part. So this is a pocket that needed repairing. And so we've been able to fill it in and not waste that part or all of the raw material that it includes. Here's a close-up look at an impeller. It looks kind of like fan blades. An impeller is what is used inside turbocharged diesel engines, and it operates a little bit like a jet engine and helps recover a lot of the energy and make your fuel consumption more efficient. Because it's in that environment, it's in the exhaust gas stream, it's very, very hot. And so as this spins, the tips of these impeller blades get worn out. Here you can see we've printed onto them. They still need to be finished, but literally those 7 or 8 or 10 layers right there have been printed to restore that tip shape. It will also be finished, and then it can be used again. Often you can re-tip these impeller blades, and the same is true of industrial gas turbines that generate electricity on the ground, or even flying turbo machinery. You can re-tip them, and often you can re-tip these parts 2 or 3 or 4 times and get 2 or 3 or 4 service lifetimes out of them at far less cost than making these parts from scratch. Here's another example. This is a blade tip that's beautifully blended in. This is after the machining step. This is an aerospace blade. And you can see on the left is the parent material, on the right is the tip. And machining very, very carefully to get a really smooth surface and very little mismatch. We always say that if you can rub your fingernail along that joint and not feel it, that it's good. Here's another example where we've taken just a base plate and added, this will be a cutting feature, that sort of figure 8 or infinity sort of shape. Those edges need to be sharpened in order to be a cutting die. But here, rather than take an entire billet and cut away most of that material in that upper section, this is where you just print what you need. And it's a far more efficient use of material. Okay, this is a hexagon pattern. Again, if I get close, you can see that as printed, it's got steps to it. You see the steps at the base of that hexagon pattern, and then it's been machined down part way. And often we would machine it all the way to the bottom. This has been left as a demo so that you can kind of see the process. So imagine this sort of mid-process after you've printed and partway through the machining step. This is a round part with a feature sticking out of it in multiple directions. To make this part conventionally, you would have to have a very, very large starting billet. Here, what's happened is this round bar, we've milled the flat surface on it, built upward, rotated it through 90 degrees, milled another flat, and built what is now sticking out sideways, this little sort of cup-shaped or P2 tube shape on it. Making it through a hybrid process really shortens the manufacturing time for this. It's a far more efficient process cycle. Here I show you again on screen this is 3D printing. You can see this deposition, and this is a lofted shape, actually 2 lofted shapes, and they're quite large, and you can print upwards. This is, again, printing somewhere. This one's probably printing at around, I'd say, 3 to 4 kilograms an hour. Here's an exhaust manifold made by one of our customers, and you can see the layers on it, and they've printed and made a curved, complex shape that otherwise is very difficult to machine or even do some types of casting on. If you look carefully at this part, you'll see there's actually different materials used in it. This is a combination of stainless, which is that center section through the middle, and aluminum bronze on the outer edges. And by using 3D printing, we're able to make parts in multiple materials. And so that multi-material capability allows you to leverage the bronze where you need it, the stainless where you need it. You get higher stiffness in some areas. You get the lubricity of bronze. This is really a powerful opportunity for designers and manufacturers to make superior parts. Not just parts that are just as good as before, but much, much better. Historically, we've often had to make separate parts when they're required to be made from different materials. Now you can add that different material where you need it the most and just do it for that small little section and join them together metallurgically, which is exciting. Okay, so you've seen kind of what hybrid manufacturing is, this combination of additive and subtractive. We've also seen that now you can use this to add a little bit of metal just where you want it, or even a little bit of polymer or composite where you want it. You can also see that you can add features onto parts or even grow parts from scratch. So there's a wide range of use for 3D printing and CNC machining, and hybrid derives from both of those. And so you get opportunities in all of the spaces that are relevant for each of those two. Let's look for a little minute about how the hybrid industry looks, some of the main players, and then we'll look a little bit at the future as well. So another question for you. What processes constitute hybrid manufacturing? Which of the following statements is true? And I'll let you just read them to yourself. All right, hopefully you're ready for the answer now. The correct answer is A. Directed energy deposition and CNC machining is certainly the most frequently implemented in industry, but it's not the only combination that makes hybrid machines. And this chart right here is a little example of that. You can see across the top this multicolored icons. These are for each of the 7 different techniques for 3D printing or additive manufacturing. You'll notice that 6 out of 7 of them have a hybrid option. This category on the far right is called directed energy deposition. It's the largest category by far and has the most adopters. If I show you carefully, this is a little view. Oops, let's see if we can get that to. This is a view of a part mid-process during hybrid manufacturing. So this is actually a forging die. And the inside edges of this die, as the material gets forged, it wears it out. So here we're actually printing back on that material that's, that would have been worn away so that it can be finished, machined, and used again. So it extends the life of this die, reconditions it. Okay, another example in terms of different types of additive is material extrusion. And here you see parts that are printed. Notice the layered and steps here on the lower section. And then at the top, we're doing cutting. Now, you've not seen a ton of video of machining, so I wanted to show this little video for you if I could. So here is a head being picked up inside of a CNC machine. Now you see deposition, and this has obviously been time-lapsed, so you can see printing quickly. It prints in a rough state. It's not to the final shape that you want, but it's close. It's oversized. And now you come back and do machining on it. In this particular part, everything can be done in a single setup. So now you can see that part has been shaped to its final shape. And it's even got, so this is a fixture for holding parts. It's got inbuilt features here and stops and other things that machinists would recognize. And with those smooth surfaces on the outside, it's now ready to be held in a chuck or another, fixturing method so that you can do downstream processing on it. So again, that's another example of material extrusion in a hybrid context. Okay, looking at a couple others, we've got a company called Fabriconic, and they do ultrasonic metal consolidation. So they're taking sheets of material rather than powder, and they use a sonotrode and use very high frequency sound to actually cause them to rub together at very, very, very high frequencies. And it actually merges those pieces of metal metallurgically. So you end up with a solid billet, and ultrasonic consolidation is a really powerful way of creating unique combinations of materials. It's a solid state process. And once you've created that, essentially a billet in the combination of metals that you want, machining is then used to finish it. Another technique that is used is binder jetting. And here you can see this is a company called 3DO. They will combine metal powder together, and while it's in its green state, so they'll combine it by essentially glue. They hold it together with glue. Then before they would fuse it, which usually when you binder jet, it's a two-step process, they then do machining on a green part, and then downstream, they fuse it all together. So kind of inverting the order of things compared to other processes, but it's really clever and it works super well on very small parts. So that's 3DO and binder jetting. Lastly, we're going to look at this orange category, powder bed fusion, which is used quite extensively. And here, this is an example of the Matsura Lumex machine. It spreads layers of powder, it fuses them, and then before it does, after it does, 5 or 10 layers, it will stop, come in with a cutting tool, and machine these surfaces smooth. So it machines them while you have access to them. And it's another great process and is used heavily in mold making to be able to do conformal channels and other things. So I hope this gives you an idea of how spread out hybrid manufacturing is across the additive manufacturing technology space. Ultimately, in each of these cases, we end up taking a single machine that can do multiple steps and allowing it to be done in a single setup, fully automated. So I know the theme of this conference has been, digitalizing. How does this really change manufacturing? And this top image is kind of the after state compared to some of what's down here below. This is a pictograph of what one of my actual customers was doing. Down along the bottom, they were moving these parts around in and out of a heater or a furnace. They were doing manual welding and automated welding. They had to cool down, do grinding. All of these steps on the bottom. This is literally a process flow. And by adopting a hybrid manufacturing approach, they were able to literally just go to one machine that swapped heads and did all of the steps in a single setup. It really was game-changing for them. It took this process right here. An average turnaround time was about 4 days for parts to make it through this process, or lead time. And they were able to drop that now to between 40 to 60 minutes. So a huge improvement in speed and also a great benefit in cost to them. And the vast majority of their production has shifted over to hybrid manufacturing because of the savings that they were able to achieve. So hybrid manufacturing, it's all digitally driven. It's 100% digitally driven. It enables flexibility and efficiency. So it helps you cope with product variability, demand volatility, a lot of what we've seen with this global pandemic on impact on supply chain and other things, as you can shorten the supply chain and the manufacturing chain, things get more reliable, more robust. So to me, hybrid manufacturing is the gathering of all the digital manufacturing techniques together and leveraging them as appropriate. Again, inspection, subtraction, and additive, these are all three categories where it's important to do that. Hybrid manufacturing enables lots of sort of the best part properties and materials on a feature-by-feature basis. So this is new capability that 3D printing and especially hybrid opens up to the world of manufacturing, where we can now intermingle those. So I show here a little, a disc on screen that's got metals and polymers and ceramics, which are the three most commonly used materials, certainly in 3D printing. Sometimes we'll expose parts only to energy to change their microstructure as well. And as you look around that wheel, you've got all sorts of opportunities to use it in different application spaces. So with a hybrid manufacturing approach, you use the best tool for the job. If milling makes the most sense, you do that. If adding makes the most sense, you do that. And where you want to use them together, that's easily done as well. And so it's really an optimization step for improving manufacturing. You can see on screen here a whole variety of different types and sizes and styles of heads. One head doesn't do everything that's needed in a manufacturing context, and most of the time one machine doesn't do it. So this is essentially a way of converging all of these different processes onto a single machine. And I'll just tell you a quick story. Part of how we came up with this idea is that I was working at a university research lab at De Montfort University in the UK. We had saved our money for a high-end 3D printer. We had a variety of printers. We'd saved our money for a high-end 3D printer. When we purchased it, it came in, and we were so excited to use it. And as we got trained on it, and I started to look around, it had a beautiful motion system on it. It could move very, very quickly, very elegantly, linear motors, and it was just a beautifully well-crafted machine. But what was really unique about it was the deposition head. And as I thought about that, I thought, we've just saved up all this money, and we bought a unique deposition head, but we've also had to purchase this motion platform. And even though it's well executed, it is another motion platform. And I looked around the lab, and we had like 8 or 9 or 10 motion platforms. And every time we wanted to buy a new type of 3D printing, we were essentially penalized because we had to then buy another motion platform that's made in small volumes and is relatively expensive. And I thought, wouldn't it be better if we could just buy the deposition head and put it on an existing motion platform that was, had high enough accuracy and fast enough dynamics that it was good? And that was really the genesis of why we said, let's do hybrid manufacturing, where we could ideally not require people to buy more motion platforms if they've already got that capability in-house. And so that was the seed that then turned into the ability to add deposition heads to existing platforms. Yes, you can buy them as turnkey solutions brand new, and you can also retrofit them. And so it's nice to be able to kind of ramp up the adoption rate through that approach. But it was born out of need, out of the pain of having saved and gotten to this point where we realized, hey, why don't we just make this available on any motion platform? So here you see examples. We've done lots of things on CNC machines, on gantries, robots, and other things in between. This is a little bit of a framework for thinking through how you hybridize things. But certainly you've got all the additive steps, which we've talked about in some detail with different colors. And then there's a whole bunch of different types of subtractive and inspection techniques that work together that are nice to be able to merge into a single setup. You certainly don't have commercial machines yet that do everything, all of the things in this chart. This is just a tool to help you think through what there could be going forward. So as promised, if you want to learn about the early history of the hybrid manufacturing market, this is kind of a snapshot timeline from it. It's about a 30 or 40 minute presentation. I'll come back to this QR code if you want to get your phones ready. If you don't have a phone that can snap a QR code, you can go to YouTube and type in hybrid CNC plus additive, 2 heads are better than 1, and that will take you to this particular link, and you'll be able to watch a little bit more about the early beginnings of hybrid manufacturing as an industry and the different players that were involved. So hopefully that's a little bonus tip for, or bonus material for you that you enjoy. And we return finally back to the beginning, where we saw these amazing structures which have lasted the test of time and were built in really using multiple modes, right? We talked about layering up those stones in a somewhat of an additive technique. And then of course the cap on top, this limestone, which is then added on top and then finished. And that finishing process involved subtractive. So I submit to you that hybrid manufacturing has its roots, at least in a manual context, going back many millennia, and these pyramids being a prime example of adding and subtracting to achieve volumetric, a large volumetric object with the ideal finish on the outside. And very, very exciting. Thank you so much for listening today. I'm happy to stay available and take questions. Again, this is what is hybrid manufacturing and how does it modernize manufacturing? Hopefully I've given you a pretty good taste of that, and I'm happy to take questions now. Thank you.
Thank you so much, Dr. Jones. We don't seem to have any questions in the chat box, but that was a very comprehensive presentation. And I did see also some requests to have your presentation emailed. So I'm guessing that they're just trying to digest the information that you presented. So thank you so much. And then next up, we have our next speaker is Ingrid Osborne. And Ingrid is familiar on this platform as she's presented also for our Women's Month. Ingrid Osborne is an electronic engineer by profession, and she's the co-founder and CEO of Cyrix Engineering Group. In 2015, Ingrid Osborne had the honor of winning the regional BWA Businesswoman of the Year award in the professional category, and now enjoys giving back to this award through judging. In 2016, Ingrid received her PR Engineering Professional Engineer accreditation through the Engineering Council of South Africa, ICSA. Ingrid has been featured in numerous publications such as Railways Africa, South African Instrumentation and Control, VentureBurn, Business Insider, South Africa Investing.com, and Business Leaders Magazine. Thank you, Ingrid, for joining us this afternoon. Over to you.
Thank you so much. It's such a pleasure to be here again. Without further ado, I think I'm going to start. I'll just share my screen and let me know if it's all good. Oops. All good.
Yes, we can see it.
All right, so my topic today is digitization of mining, the adoption of automation in mining to improve safety and increase efficiency. And I'm really here today as an engineer, someone who has both experienced the health and safety activities on site, good and bad, unfortunately. And as someone who has implemented digital document solutions or compliance solutions on these sites to specifically advance health, safety, and document legal compliance. So when I say I'm talking about the adoption of automation to improve safety and increase efficiency, I'm talking about digital automated document management, contractor management, complete site legal compliance. There are so many aspects of automation that we could talk about here, but I really feel that before you start to automate, you need to get the right digital compliance systems in place. In such a dangerous environment, it's critical to have these systems up and running first to truly achieve safety and increase efficiency. And it's amazing how many sites don't. So the Leon Commission was set up in 1994 by South Africa's post-apartheid democratic government, firstly to look at safety and health in the mining industry and to make recommendations to improve the standards that had been set. And it found that there were an estimated 69,000 fatalities and 1 million injuries on South African mines between the 1900s and 1993. The Commission also found that the old legislative framework governing mine health and safety was completely insufficient. The laws that were in place had not been properly enforced by government, and the mining industry had been allowed to disregard key aspects of existing laws. So beside what the Commission called an appalling accident record, there were serious occupational health problems in the industry, with high incidence of tuberculosis, silicosis, asbestos-related diseases and the like. It was also noted that the Mine Health and Safety Inspectorate was under-resourced. Urgent remedial action was needed. The Commission resulted in the endorsement of the Mine Health and Safety Act 29 of 1996. South Africa's transition out of apartheid after 1994 included the creation of a new constitution in 1996 and is widely regarded as the most progressive in the world. Section 24 of the Bill of Rights of the Constitution of the Republic of South Africa in 1996 includes the following statement: everyone has a right to an environment that is not harmful to their health and well-being, which must also be applied to the work environment. So John Kane Berman wrote an article in Mining Essay called Then, Now, and Into the Future. He wrote this in February 2017, and he had a wonderful passage which went like this: people think nothing of stepping into a lift and pressing a button that will take them within a minute or two to the top of the tallest buildings in the world. Yet the world's deepest gold mine, Maponeng, outside Carletonville in Northwest, is almost 5 times as deep as the world's tallest skyscraper in Dubai is tall. Finding gold at these levels in the first place, sinking shafts, cooling rock faces, lowering thousands of men below the surface and then bringing them safely back up again, and hauling thousands of tons of rock to the surface as a routine daily activity is a feat of enormous human ingenuity. Mining is probably one of the most dangerous occupations of our time, and mining disasters are littered throughout our history. A coal mine in China in 1942, 1,549 miners died as a result of a fire. And according to one study, China in 2003 accounted for 80% of coal mining fatalities, even though it only produced 35% of the world's coal. The worst disaster in South Africa occurred in 1960, when 437 miners died at the Colebrook Colliery near Sasolburg in a massive ground collapse. 177 people were killed in the Kinross mine in Evander, Mpumalanga in September 1986. An acetylene tank sparked flames that cleared through the mining tunnel. It ignited the plastic coverings on the wiring. The flames set fire to the polyurethane foam that was used to keep the walls dry. The miners were choked to death by toxic fumes from the combination of the burning plastic and the polyurethane. 104 deaths in May 1995 at Vole Reef, where an underground locomotive carriage fell down a lift shaft and landed on top of a cage loaded with night shift miners. Although South Africa's mining industry has been aimed to reduce mine fatalities to zero, in July this year, according to FIN24 report, the Mineral Council of South Africa said that a total of 32 mine workers had already died to date in 2021 in the country's mines, an increase from the rate this time last year. The number of SA mining fatalities in 2018 stood at 81. 2019 was recorded as the safest on record with 51 deaths. In 2020, as the industry navigated the emergence of the COVID-19 pandemic, which hobbled full capacity operations in the initial months of the hard lockdown, some 58 mine workers were killed in accidents. Worse news still is that the International Council on Mining and Metals found in its 2020 report that South Africa had accounted for half its members' fatalities. Their latest safety performance report finds that South African members of the Council had the highest fatality rate last year, accounting for 50% of the reported fatalities internationally. So we have to ask why these numbers are still so high and where we're going wrong. M.A. Hermanus wrote an article, The Journey of South African Institute of Mining and Metal, in August 1917, and said, the recent developments, such as the increasing number of contractors working on mines, the emergency of junior mining companies, and the recognition of small-scale and artisanal mining, pose new challenges for health and safety regulation and practice. And he cited examples such as, with more contractors and contracting companies on site, occupational health and safety is more complex, given the need for contractors to, quote, competitively for work. The tensions between health and safety goals and production outputs are heightened. Many junior mining companies lack the resources for larger counterparts to identify best practices for health and safety and to develop comprehensive approaches to risk management. And until recently, artisanal and small-scale mines, which play a role in poverty alleviation by providing employment, were not catered for in the South African mining policy. About 20,000 small-scale and artisanal miners are active in the country. Small-scale and artisanal miners often lack business management skills, awareness of the legal compliance for mining, and the means to address health and safety risks. A cost and loss revenue of safety stoppages issued under Section 54 of the Mine Health and Safety Act between 2012 and 2015, 13.6 billion rand. And that excluded the losses incurred in restarting mines. So now more than ever, the adoption of automated and digital solutions to improve health, safety, and efficiency is essential. Companies need a digital health and safety management solution to ensure that both the company, its workers, and contractors are protected. A solution aimed at driving business success. So in 1911, miners in Great Britain carried a canary into the cage down into the mines with them. The carbon monoxide in the mine can build to deadly levels, but it has no smell. So if the canary weakened or stopped singing, miners knew to get out of the mine quickly. So why use a bird instead of, say, a mouse? That had to do with the bird's breathing anatomy. Canaries get a dose of air when they inhale and when they exhale, thus a double dose of the toxic gases. Thankfully, in 1986, more humane electronic warning devices replaced them. Pit ponies, the other animal that went underground with human miners to haul coal, were also phased out by automation. The last of them retired in 1999. Autonomous equipment replacing these ponies and birds and making it more efficient and safer. Social and environmental concerns are also compelling mining to look for safer, more efficient, and sustainable ways of conducting the business. Reduction of energy and water consumption, lower emissions, and waste generations are all factors that are core to the mine of the future. But in spite of this, all this advancement we've made, in Jan 2020, in his statement on the release of the 2019 Mine Health and Safety Stats, Minister Gwede Mantashe noted that the increase in fatalities and injuries during the first period of that year was mainly attributed to production pressures associated with performance incentives, poor supervision, and complacency. Basically, human error. Technological advancements have successfully decreased the number of injuries and fatalities, but these numbers continue to remain unacceptably high in South Africa. Human error is a major safety factor for every industry, and miners can be especially prone to this. In a study done called Research to Determine the Frequency and Cause of Injury, Accidents in Underground Mining by Saunders and Shaw, it concluded that human error of the injured employee was involved to some degree in 93% of the cases. I love the way the Professor of Psychology, Dr. James Reason, in the British Medical Journal, looks at workplace accidents. You could look at human errors that lead to workplace accidents in one or two ways: the personal approach or the system approach. The personal approach focuses on the errors of the individuals, blaming them for their forgetfulness, inattention, or moral weakness. The emphasis is on the unsafe acts. The system approach concentrates on the conditions under which individuals work and tries to build defenses to avert errors or mitigate their effects. The person approach emphasizes unsafe acts resulting from slips, lapses, mistakes, and violations of safety rules. The person approach blames the errors that lead to these accidents on human failings, such as forgetfulness, inattention, poor motivation, carelessness, negligence, and recklessness. The problem with this is that even the best people make the worst mistakes. The system approach, on the other hand, recognizes that humans are fallible and errors are to be expected, even in the best organizations. Preventing workplace accidents under a system approach is based on the assumption that though you can't change the human condition, you can change the conditions under which the employees work. By creating a system for managing existing threats in the mining environment that is accessible to everyone, we can mitigate human error. Companies in the mining industry can address sector-specific issues and provide a safe working environment for employees. Sometimes we focus on human error in the production environment, but human error starts long before that with your health and safety system, which is supposed to back you up. By automating this, you have a good, solid start to solving an incredibly complex problem. To eliminate human error, we need to digitize and we need to automate. As technologies evolve, we need to adapt and adopt. There is no doubt that automation and digitization is faster, cheaper, and safer. Ensuring the safety and health of all mining employees and contractors requires active collaboration between management, employees, contractors, and regulators. And let's just take a minute here and look at regulators. Why include regulators? They don't pay fines and they're not on site. Because everyone, every stakeholder needs protection, and even sometimes from themselves. Going back to the John K. Berman Mining and SA article, Then, Now, and Into the Future, he describes a case from 2016 as follows. In November 2016, the Labour Court overturned an order shutting down a mine near Orkney in the Northwest Province. In his judgment, Andre van Niekerk said that the order, which was causing losses to the company of 9.5 million rand a day, had been out of all proportion to the problems identified. This was because it prohibited various operations across the entire mine, even though no reasonable person would believe that infractions on a minute part of it endangered the health and safety of everyone on the rest of the mine. Judge van Niekerk said that the Mine Health and Safety Act had as its commendable purpose the protection of the health and safety of employees in mining, but that this did not entitle those responsible for enforcing the act to act outside the bounds of rationality. And he added that if the company had sought an order, that the mine inspectors concerned should bear the costs of the legal action in their personal capacity, he would have given serious consideration to such an order. Alan Seccombe, resources writer on the Business Day, wrote after that case that some companies were contemplating suing incompetent and malicious inspectors in their personal capacities when they acted in bad faith. So if there was a robust system in place that included all stakeholders, such as regulators, and that everyone agreed to, this would eliminate hostilities between these stakeholders. You'd want an inspector to look at a system and say, you have everything in place. You've really tried your best. In order to improve health and safety in mining, we need to start to look at systems in place where possible, and where possible, eliminate human error and create a reliable, transparent, inclusive platform for every stakeholder within the organization. And one place to start, and the one place most overlooked, is the actual health and safety system itself that manages compliance of its employees, of its contractors, of its processes, of the company, of its equipment. If it's not already a digital system, then our case study shows that you're probably sitting at 35% compliance. And if there is an accident or an incident on site, you'd better hope that it resides within the 35 compliance you do have in place. The risks that are associated with non-digital, non-automated health and safety management systems are big enough to warrant a thorough investigation into a viable solution. Generally, when a stop notice is issued under Section 54 of the Mine Health and Safety Act, this causes losses to the company of millions of rands per day. This is what you want to mitigate. If a stoppage is issued, you want to be able to access the necessary data and documentation as quickly as possible and efficiently as possible. We have a case study where, after a stoppage has been issued, using a digital health and safety management system, the investigations were concluded and the entity up and running in half the amount of time it generally took. And it included the addition of further corrective measures within the system. Adoption of automation in mining to improve safety and increase efficiency starts with legal document compliance. Safety on mines is a concern for everyone. Employees, contractors, managers, and regulators. Everyone needs to be involved in order for us to improve safety on mines. Contractors and employees should be able to self-monitor their compliance, have access to mobile solutions to capture near misses or record an incident, have real-time notifications and dashboard reporting. Teams should be able to see their data stats and measure themselves. The system should automatically notify of missing or outdated documents long before they ever outdated. There should be a history and an audit trail of document approvals or rejections. And when you have a digital solution, you can use the system to cater for other needs that arise, such as a COVID-19 tracker or wellness system. If everyone has access to an existing system, adding on a wellness tracker is quick and easy, an extension of the existing system. And as other problematic areas arrive, the system can then expand to close these gaps, eliminate human error, and evolve as a living system. A digital system also sets out standards and fixed unattainable targets or requirements, which can be applied across the board. And this is essential if you're a mine or a regulator. There is no need for opinion calls. Junior miners, for example, can make use of an existing digital solution that does not require additional resources and expertise, that prompts the companies for their document requirements, that shows them exactly what their percentage compliance looks like, and regulators can then use this data to see who needs assistance before any accidents or fatalities can occur. Having an internal system available to all employees and contractors encourages awareness and accountability. Suddenly a task in terms of legal compliance, which seems enormous and even overwhelming at times, is doable and sustainable. A safety management system is woven into the fabric of an organization. It becomes part of the culture, the way people do their jobs. And it should not be a system few people have access to. It should be something everyone uses each and every day for a better safety outcome. And once this robust system is in place, this allows you to start to treat the causes rather than the symptoms. With a connected workforce and people sharing information, digital automated solutions can inform management and workers on what's happening in operations, allowing them to better adjust production and troubleshoot problems. Given the dangerous working conditions on the ground and the risk to the local environment, this data can then lead to additional connected sensors, monitors, and alarms in the field, which then become key tools for reporting potentially harmful events and conditions, and quickly alerting employees and leadership to possible issues. Technology has made the implementation of an authorized or an automated health and safety system easy and doable. We just need the will to do it. Software as a service models have made these solutions inexpensive, and for smaller companies can cost as little as 450 Rand per month. So as much as we need autonomous vehicles and other intelligent devices, we need to take care of the basics. Get the basics right. If we cannot get our compliance documentation in place and within a digital space, we are pulling the cart before the horse. It all starts with regulation and compliance. The correct training for workers and the associated documentation to verify this, medicals and competencies, company document legal compliance, following the mining regulations. This all needs to be tied into a digital document system. And then the system needs to evolve to the needs of the environment, the company, and its workers. We need a connected mining environment. We need to connect regulators, management, employees, and contractors for us to reach the goal of the target of zero harm in the mining industry. And the companies who are looking to make the change, the digital first movers, they are our modern day heroes. I hope you've all enjoyed that. I'm happy to answer any questions that you may have.
Thank you so much, Ingrid. Thank you for that presentation. I don't see any questions at the moment in the chat box, but if I can please ask you to write down your details in the chat box so that we can have any questions then sent to you. We are currently just waiting for our last speaker who's experiencing some technical difficulties. Okay, it seems that unfortunately our last speaker is unable to join us due to the technical difficulties that he's experiencing. But what we would request then that he does is that he sends us his presentation so you don't miss out on what he was going to talk about.
Hi, Ivashni. It looks like we're not going to be able to get Hugo online at this point. He's got some connection issues. So apologies for that.
Okay. All right. Thank you, everyone. Sorry about that. Unfortunately, we aren't able to get Hugo on. But thank you, everyone, for joining us. Ingrid, you have a comment regarding your presentation as well. Great presentation indeed. So thank you, everyone. Thank you to all our attendees. Thank you to all our speakers. We really appreciated having you over the last 2 days. And we would like to encourage everyone also to look out for our CPD accredited workshops in October. If you would like to participate as an attendee or as a speaker, please let us know and we can let you know how to get involved. And also, we look forward to obviously seeing you at the physical event of AATF in 2023. Thank you and have a good day. Bye-bye.